the following Thursday. The details will be on the website, but it'll be a 3-hour self-timed exam. You can use book, notes, and I don't really think it'll take you 3 hours, but that's how much time you'll have. We were talking about quantum ideal gases. Which we analyze using the Fermi-Dirac and Bose-Einstein distribution functions, which tell us the expected number of particles in an orbital with energy E when the chemical potential is mu and the temperature is tau. This plus or minus sign, that's one of the most important minus signs in physics. It's plus for fermions, minus for bosons. When the occupation number is low, we're in the so-called classical regime, where this is just proportional to a Boltzmann factor. But we're interested in the case where the occupation number isn't necessarily small now, and that's what I mean by quantum ideal gases. We talked about the case of a degenerate Fermi gas. That's the case of strictly zero temperature, where the occupation number is 1 for all energies up to the chemical potential, which at zero energy is called, zero temperature is called the Fermi energy, and all the higher orbitals with energy above the Fermi energy are empty. Now, we know that counting orbitals can be expressed as, well, in d dimensions, it would be a d-dimensional spatial volume divided by 2 pi to the d times a d-dimensional wave number integral times a possible spin factor. In the case, well, I could write that in particular. In the case of non-relativistic particles in 3 dimensions, as volume over 4 pi squared, 2m over h bar squared to the 3 halves, energy to the 1 half, d energy times the spin factor. So in the case of electrons, for example, or spin 1 half fermions, there are 2 spin states, so the spin factor is 2. So in the degenerate case, we can say that we fill up all the orbitals up to some maximum value of the wave number, the Fermi wave number, just by integrating that density of orbitals and including the spin factor. We see that the Fermi wave number cubed can be written as 3 pi squared number of particles per unit volume. And the corresponding Fermi energy or chemical potential is the energy associated with that wave number, h bar squared k squared over 2m, where k is the Fermi wave number, which is therefore h bar squared over 2m, 3 pi squared n to the 2/3 power, where now little n is number per volume. The internal energy, then just adding up the energy from all the occupied orbitals up to energy EF, is 3/5 number of particles times the Fermi energy. So the average energy for the particles in the filled orbitals is 3/5 the Fermi energy. Again, 3 dimensions, non-relativistic particles, spin factor 2. Then we talked about the nearly degenerate case. That means the temperature is not 0, but it is small compared to the Fermi energy. And in that case, the step in the distribution function at 0 temperature becomes rounded a little bit. So there are some orbitals close to but below the Fermi energy for which the occupation number is a bit less than 1, and some orbitals just above the Fermi energy where the occupation number, though less than 1/2, is not strictly 0. And the width of the range in energy in which we have occupation numbers that differ appreciably from 1 and 0 is about the temperature. Now, thermally, we can excite some particles that are just below the Fermi energy, pushing them up to just above the Fermi energy, and we get this rounded distribution. Or just above and just below means by about an energy equal to the temperature. And then we said that if we consider the internal energy in that case, it'll be whatever it is at 0 temperature. So constant means independent of temperature, but then plus something, well, which is some numerical constant times temperature squared divided by Fermi energy times number of particles. So again, the picture is that there's some fraction of the particles which are now excited, but that fraction is about tau over EF. It's only the orbitals that are close to the Fermi energy in a band with thickness about equal to the temperature, and they're excited by an amount which is about the temperature. So it's tau times tau over EF, and proportional to the total number of particles. And so correspondingly, the heat capacity, du d tau, has a term which is the leading term for small temperature, which is proportional to tau over EF times the number of particles, plus higher order in the temperature, order tau squared, etc. And I said equals, but actually there's a number there, and we computed it. The coefficient of tau over EFN in the heat capacity we saw was pi squared over 2. So in metals, there's a contribution to the heat capacity that comes from the nearly degenerate electron gas. There's also a contribution that comes from the phonons, which we've talked about before. So the heat capacity is some number, and we've seen that it's pi squared over 2 tau over EF times the temperature, plus contributions from the electrons that are higher order in tau. But there's also a contribution that comes from the Debye theory, which is proportional to temperature cubed. And at low temperature, these tend to be the leading contributions. We know what gamma is. I just told you that it's pi squared over 2 n over EF. And we know what A is from Debye theory. This is the electron contribution. Whoa. And the Debye theory contribution, which goes like tau cubed at low temperature, has a coefficient which is, we saw to be 12 pi to the 4 over 5, and Debye temperature to the minus cube. Now remember, the Fermi energy in a typical solid is at the order of electron volts. And so that's a pretty big temperature compared to room temperature. An electron volt is about 10,000 degrees K. Compared to room temperature, which is about 300 degrees. And a typical value of the Debye temperature is some number of order 1 times 100 degrees. Of course, it's because this Fermi energy is large compared to room temperature that we can say the electrons are nearly degenerate typically. And so we can use our formula. Use the leading term in an expansion in temperature. And then we can ask, where do these two things cross over? There's a linear contribution from the electrons, the cubic contribution from the phonons, and they typically cross over at about 1 degree K. At lower temperatures, then the linear term is dominant, and experimentally, the linear behavior of heat capacity at low temperature is seen pretty accurately. Okay, so I think that's pretty much where we left off. Now let's talk about another application of the theory of nearly degenerate electron gases, and that is white dwarfs. I know it seems like they should be called white dwarves, but they're usually called white dwarfs. White dwarfs are little stars. Back in the 19th century, astronomers looking at Sirius, a nearby star, like other nearby stars, it moves across the sky relative to the more distant stars, but it moves in a funny way. It wiggles. It doesn't go in a straight line. Why does it wiggle? That's right. Sirius, or Sirius A, the bright star, has a relatively dim companion, which is called Sirius B, and they are rotating around one another. Okay? Or I guess you call that revolving. Anyway, they're in orbit around one another. And from the orbital dynamics, we can say something about the companion, even though at least initially it was hard to see. You can see it, get a nice picture of it if you know where to look. Nowadays, with the Hubble Space Telescope, you can get nice images of this and other binary star systems. Even in the 19th century, they were able to look at Sirius B. This is called the dog star, so this is the pup. And you can see that although it's about 8,000 times dimmer than Sirius, it's there, it's shining, and we know its mass because we know the orbital period from the way it's wiggling, and from the size of the wiggles we know something about the distance between the two stars in this binary. So it turns out that Sirius B has a mass which is pretty close to the mass of the Sun, which is what? Anybody know the mass of the Sun? All right, you have 2 times 10 to the 30 kilograms. Well, you need to think about it. And now, we also know something about the area of Sirius B. How do we know that? How big it is? I mean, nowadays you can actually take a picture of it. But back then it was just like a point. But you could measure how much light it was emitting, what its luminosity is. Okay? So you could see how bright it is. You could also see what? From the light has a color, right? And the color tells you something. It tells you it's emitting like a black body. Right. So we know the temperature. We know the luminosity. And the luminosity is given by Stefan Boltzmann, right? Because it's the Stefan Boltzmann constant times temperature to the 4 times the area of the surface of the star. It's emitting like a black body at some known temperature. We know what the luminosity is, and therefore we can figure out what the area is. So we know how big Sirius B is. And how big is it? Anybody know how big it is? Well, how big is the sun? Anybody know how big the sun is? What's the radius of the sun? Yeah, okay, so the radius of the sun is about 700,000 kilometers. And how big is the Earth? Yeah, it's like 100 times smaller. And this guy, Sirius B, we can infer from the temperature and the luminosity, has a radius which is about 20,000 kilometers. Yet it's about the mass of the sun. Okay? So it's not much bigger than the Earth. It weighs as much as the sun, which is about, 1 million times the mass of the Earth. So it's very dense. The mass density, the average mass density, which of course varies in depth from the surface, but the mass divided by its volume is about 7 times 10 to the 4 grams per cubic centimeter. So, it's about 70,000 times denser than water. Right? Pretty dense. So what's holding it up, right? There's very strong gravity trying to pull in the stellar material, but it doesn't collapse. It's stiff. What's making it stiff? What did we just learn about? What's making the star stiff is electron degeneracy. And we can speak of degeneracy pressure. Gravity is trying to make it collapse, but the pressure in the material is resisting the collapse. But the origin of that pressure is that the electrons in the star are a nearly degenerate Fermi gas. So since we know the density, let's suppose it's uniform. It's not really, but it's not such a bad approximation. We know the volume, so we should be able to, since we know the mass of the electron, to compute the Fermi energy. And I guess I'll tell you what it is. It's 3 times 10 to the 5th electron volts. So that would be like 3 times 10 to the 9 degrees Kelvin. That's a high energy, right? I mean, like, what's the temperature in the core of the sun? It's a lot less than this, right? Maybe it's 10 to the 7 degrees K or something like that. This is a really high energy. And so even in the core of the white dwarf, the temperature is small compared to this Fermi energy. So we have temperature much less than Fermi energy. It's nearly degenerate. Actually, well, compare this energy, this Fermi energy, to Rydberg. Somebody told me last time what that is, right? What's Rydberg? The binding energy of hydrogen. Yeah, it's 13.6 eV. So this is huge compared to that. All these electrons are in this nearly degenerate gas, and there are a bunch of protons around. Are they bound? Are the electrons bound to the protons, like in neutral hydrogen? No, they're going to ionize, because the Fermi energy, that's their kinetic energy in this gas. It's huge compared to the binding energy. The protons are just like little bumps that they hardly notice. It's pretty much like an ideal electron gas. Okay. In fact, it's not that different from mc squared for the electron. What's that, by the way, in electron volts?
511.
Oh, yeah. That's 511 electron volts, and so that's not right. That's keV. keV. And, this was about 300 keV, so it's comparable, right? So it's not really a non-relativistic gas. Actually, we'll come back to that. But it's not so bad to treat it as non-relativistic to get some order of magnitude estimates. So let's try to see if we can understand the size of Sirius B. Why is it 20,000 kilometers? And if you really want to do this right, you should take into account that the density of the star is not uniform. It's more dense closer to its center than at the surface, and you can figure out how that goes, but it'll change some numbers of order 1. But let's forget about the numbers of order 1 for the purpose of this estimate. That'll be nice. I won't have to worry about things like 4 pi squared, 3 pi squared. I'll just set them equal to 1 to kind of get a feel for how things go. So what's going to determine the size of the star? Well, suppose we say the energy is the kinetic energy plus the potential energy. So this will be the internal energy of an essentially degenerate electron gas. And this will be the gravitational potential energy of the star. Well, the gravitational potential energy, I can just take as though it were a spherical shell in my order of magnitude estimate. It's Newton's constant times mass squared over r. And for the kinetic energy, I'll use this internal energy that I estimated here, but I don't care about the 3/5 for my current estimate because I'm making other approximations that are as bad as ignoring the 3/5. So it's essentially n times the Fermi energy, and the Fermi energy goes like h bar squared over m, because I don't care about the 2, times the density or concentration to the 2/3. So I can take the kinetic energy to be n, h bar squared over the mass of the electron, because I'm talking about the electron degeneracy pressure, and the k squared I can write as number per unit volume to the 2/3. So actually altogether that goes like n to the 5/3 divided by r squared, because it's volume to the 2/3. Okay? I guess that's right. So this is cool, because the gravitational potential energy goes like 1 over r, except it's negative, right? And the kinetic energy goes like 1 over r squared. So the kinetic energy is going to become more important when the star is small. The energy, which is the sum of kinetic energy and potential energy, will be going like 1 over r squared for small r. Then it'll go like minus 1 over r for large r, because it'll be dominated by the gravitational piece. So this is energy combined potential and kinetic energy as a function of the radius. So the star is going to want to sit here at the minimum, and we'd like to estimate what that is. That's our estimated size of Sirius B. So this function, kinetic energy plus potential energy, h bar squared over mass of the electron. The n is the number of electrons, but it's essentially the number of protons. And so I can take n to be the total mass divided by the mass of the proton, So that's raised to the 5/3. And then I have the 1 over r squared. Well, that's the kinetic energy, and then minus gm squared over r for the potential energy. And so I want to know where the minimum is. I can differentiate that and set it equal to 0, and since I'm not being careful about things like factors of 2 anyway, I can say it's minimized at a value of r, which up to factors of order 1 is going to be 1 over gm squared h bar squared over me, mass over proton mass to the 5/3. So if I just differentiate with respect to r and set it equal to 0, I get something like that. So that means our estimate is h bar squared over Newton's constant g. I have a mass of the electron coming from the kinetic energy of the electron. I have a mass of the proton to the 5/3 coming from here. And then I've got a 1 over m squared here and an m to the 5/3 here. So actually it goes like m to the minus 1/3. When the star gets more massive, it actually shrinks. Okay? And that's because we have a higher power of the mass in the potential energy than in the kinetic energy. Okay? And if you put in our estimate of the star's mass, 2 times 10 to the 30 kilograms, well, I'm just trying to do orders of magnitude. If you put in numbers, I can write this as 10 to the 20 grams to the 1/3 centimeters, mass to the minus 1/3, and then if I put in the mass of about 10 to the 33 grams, that'll give me a radius, which is the cube root of 10 to the 33 is 10 to the 11, so it's about 10 to the 9 centimeters, which is 10 to the 4 kilometers. So we're getting the right answer up to a factor of 2, which is about as well as we expect it to do. Okay? It is much smaller than the Sun. It's comparable in size to the Earth when the electron degeneracy pressure balances the inward gravitational pull. Okay. So now let's come back and think about the fact that this Fermi energy is actually comparable to the rest energy of the electron. So as we get a more massive star and a denser star, the Fermi energy goes up. Eventually we're really in the relativistic regime, where we're better off using relativistic kinematics than non-relativistic kinematics for relating the wave number and the energy. So what happens when we're in the extreme relativistic regime? So if it's a relativistic Fermi gas, now the Fermi energy, which is the Fermi momentum times c instead of p squared over 2m, is h bar c times the Fermi wave number. Well, I can still say, since our counting of state still applies, again, not worrying about pi's and factors of 4 to 1, that the number of particles per volume goes like the Fermi momentum cubed. And for the energy per unit volume, I can integrate up to k Fermi dk k squared, and I'm not keeping the 4 pi squared, but then the energy when the wave number is k will now be h bar ck instead of h bar squared k squared over 2m, because it's a relativistic particle, not a non-relativistic particle. And so this goes like h bar c from here, and now the integral is proportional to k Fermi to the 4th. And k Fermi is the Fermi energy divided by h bar c. So if I want to write the energy per volume in terms of the Fermi energy, plugging in for k Fermi to the 4th, I get 3 powers in the denominator, since there's 1 power in the numerator, of h bar c, and then the Fermi energy to the 4th power. Well, of course, that looks a lot like black body radiation. For which we had a similar looking formula with the energy per volume going like 1 over h bar c cubed times temperature to the 4th. Here we're really considering a degenerate gas at 0 temperature, and for the black body radiation, the typical kinetic energy of the photons was fixed by the temperature, but here it's fixed by the Fermi energy, right? Okay. So, in other words, the total energy of the gas goes like h bar c times volume times k Fermi to the 4th, and we have k Fermi cubed going like n over b, so it's h bar c times volume n over v to the 4/3, or everything's approximate, h bar c, and then I have n to the 4/3, and volume to the minus 1/3, so it's n to the 4/3 times 1 over r for the kinetic energy. Once we get to the extreme relativistic regime, the kinetic energy, which when the gas is non-relativistic goes like 1 over r squared, now goes like 1 over r. So does the gravitational potential energy. Okay? So once the gas gets dense enough, the question becomes which contribution of order 1 over r, the gravitational potential energy, which is negative, or the kinetic energy, which is positive, which one wins? And that will determine whether the star is stable or not. If the gravitational potential energy wins, it'll want to collapse and go to smaller r. If the kinetic energy wins, it won't. So, gravitational potential energy really its absolute value, because it's negative, will be greater than kinetic energy if the coefficient of 1 over r in the gravitational potential energy, which is gm squared, beats the coefficient of 1 over r here. So the star is unstable, and therefore collapses to a smaller radius if gm squared, the coefficient of 1 over r in the potential energy, is greater than something which, neglecting orders of order 1, I can write as h bar c. And to n to the 4/3, again, I will say the number of electrons goes like the number of protons, which is the total mass of the star, which is dominated by the protons, because they're much heavier than electrons, to the 4/3. So the condition for stability, that's actually, that inequality, if it's satisfied, means the star is unstable. And because the left-hand side goes like m squared and the right-hand side like m to the 4/3, once the mass is large enough, it'll be unstable. So, condition for stability is the mass has to be greater than some value. I'll call it the Chandra mass, which stands for Chandrasekhar, but that's too hard to say, so we call it Chandra. And what is it? Again, up to factors of order 1 that we haven't kept track of. Well, we've just seen that the Chandra mass, Chandrasekhar mass, to the 2/3, if I divide both sides by m to the 4/3, I have m to the 2/3. Goes like h bar c divided by g, and then mass of the proton to the minus 4/3. This mass of the proton to the minus 4/3. So I can write that, therefore, this way: the Chandra mass is h bar c over g to the 3/2, 1 over the proton mass squared. So this is something which has the dimensions of mass cubed. H bar c over g to the 1/2 is a mass. We can make something with the dimensions of mass out of those fundamental constants, h bar, c, and g. Anybody know what that mass is called? Yeah, we call it the Planck mass. And anybody know what it is numerically? In grams, it's 10 to the minus 5 grams. Planck was excited about this because he realized actually in 1899, before he discovered the radiation law, that there was going to be a new fundamental constant, which later turned out to be h bar, that had to appear when the radiation law was pinned down. And with that fundamental constant together with c and g, he could make units for anything: length, time, mass. And he noted that there was this, he guessed that h bar would be of the order of magnitude it turned out to be, and realized about an order of magnitude what that mass would turn out to be. It's the Planck mass, 10 to the minus 5 grams. So for the Chandra mass, there's some number which we haven't been careful enough to compute, but Chandrasekhar was that careful. And we have the Planck mass, and then the ratio of the Planck mass to the proton mass squared. So that ratio, since the proton mass is 10 to the minus 24 grams, is about 10 to the 19. When I square that, I get 10 to the 38. And this is 10 to the minus 5 in grams. So this turns out to be about 10 to the 33 grams, or about the mass of the sun. So a star which is much heavier than the mass of the sun won't be supported by electron degeneracy pressure, as it'll be so compressed that the electrons will become relativistic and it'll collapse. When Chandrasekhar does the calculation a little more carefully, he finds that the actual value is about 1.4 solar masses. Okay? Oh, we weren't too far off. And in fact, no one has seen white dwarfs that are heavier than that. Although we know lots of white dwarfs, or dwarfs, by now. So, what happens then? What if the star is heavier than Chandrasekhar mass, tries to be a white dwarf, but it can't be supported, it collapses, and then what? It collapses to what? It can be a neutron star. All right, let's think about that a minute. So we've got this gas of electrons, and they're very compressed. They have very high Fermi energy. They'd like to get to a lower energy state. And there's a way for them to do that. They have a wonderful way called inverse beta decay. A proton and an electron can become a neutron and a neutrino. Okay? And that's a great way of getting rid of electrons, which are light, in favor of neutrons, which are heavy, and neutrinos, which interact very weakly and can escape from the star. And when the star gets dense and hot enough, this process proceeds. Why doesn't it happen to ordinary matter? Why, hydrogen is a proton and electron. Why doesn't it just combine to give a neutron and a neutrino?
The chances of the electron being with a nucleus are really, really small.
Well, that's true, but there's another reason, which just has to do with kinematics. What's the mass difference between the neutron and the proton? What's the mass of a proton, roughly, in keV? It's about, isn't it about 938 MeV? About a GeV. A neutron is heavier than a proton by about 1.3 MeV. Somebody already told me that the mass of an electron is 0.511 MeV. Okay, so it's just not kinematically favored, unless you had a lot of energy, for a proton and electron to make a neutron. Okay? So why can it happen in this very dense star? It doesn't happen in ordinary hydrogen here on Earth.
Electrons have a lot of energy.
Well, the point is that once we have this highly degenerate electron gas, the electrons have a huge amount of kinetic energy when they're in the gas, right? Once it gets to be relativistic, the Fermi energy of the electrons gets to be above an MeV, big enough so that we can actually reduce the energy by having the electron combine with the proton to give a neutron. Even though the neutron is heavier, we gain more in reduced kinetic energy of the electrons than we gain in the mass when the proton becomes a neutron. Okay? And so this process can then go. And so then what's going to stop it? Well, what can stop it is the neutrons are fermions too. Okay, now we got all these neutrons, and they will eventually form a degenerate gas. Right? And then what's going to hold the star up will be neutron degeneracy pressure. And that's what happens in a neutron star. So how's the neutron star going to be different from the white dwarf? Well, again, if we use our non-relativistic approximation, we can do the same calculation as before. And the only difference is this. In the kinetic energy now, we won't have the mass of the electron. We'll have the mass of the neutron, because now we're talking about the neutron kinetic energy, right? Okay. So, that means that the radius of the white dwarf is going to be given by a similar formula, but we'll have the mass of the neutron in the denominator, because the kinetic energy goes like p squared over the mass of the neutron times the stuff we had before, 1 over gm squared number, which I can take to be total mass of star divided by mass of neutron to the 5/3. So the important difference is, now we have 1 over the mass of the neutron. Well, how much heavier is a neutron than an electron? A lot heavier. I have the formulas on the board. It's about 1,800 times heavier. Okay, so the radius of the white dwarf is going to be something like 1 over 18, neutron star. It's going to be a lot smaller because it's neutron degeneracy pressure that's holding it up. And since we estimated something like this before, now we're going to be below 10 kilometers. It'll just be a few kilometers. I'll say of order 10 kilometers. Okay? Think about that. It's the mass of the sun, and it's it's like the size of a mountain, but it's got the whole mass of the sun in it. So how dense is that? It's pretty close to the density of nuclear matter. It's nothing but neutrons forming a thick, rich soup. So the density goes like the density of nuclear matter, or the density of an atomic nucleus. It's now about 1 billion times denser than this white dwarf stuff, because we've shrunk the radius by a factor of about 1,000. Okay? Now, when the white dwarf collapses, or a star collapses, and it becomes a neutron star, there's a lot of energy released. Why is that? Where did all that energy come from? Right. Its gravitational potential energy went down by an enormous amount, and all that energy gets released. So energy of the order of gm squared over r neutron star gets released. Anybody have an idea how much energy that is? Well, I don't mind telling you. It's about 10 to the 53 ergs. Is that a lot of energy? Does anybody know the luminosity of the sun? How many ergs is the sun putting out every second? The luminosity of the sun is about 4 times 10 to the 33 ergs per second. So in its whole lifetime, how it's been around, 10 to the 18 seconds or something like that. In its whole lifetime, the energy it's put out is smaller than 10 to the 53 ergs by at least an order of magnitude. How long do you think it takes for this energy to get out of that star when it collapses? It takes about 10 seconds. 10 to the 53 ergs released in 10 seconds. More than 10 times the total energy the sun emits in its lifetime, and it comes out in 10 seconds. Do you think you'd be able to see something like that if it happened? Well, if they were close by, you would. And what do we call it? It's a supernova. actually, most of that energy comes out in the form of neutrinos. Most of it just escapes as neutrinos. And, however, this stuff is so dense, normally neutrinos can, go through a light year of lead without interacting, because they're that weakly interacting. If they, like the neutrino with a typical energy in this inverse beta decay. But this stuff is so dense that the neutrinos get scattered many times on their way out. That means some of their energy gets deposited in the matter in the star. And so what do you think happens to the star? It blows up. That's what happens in a supernova. The star explodes. And exactly how it does that, we still don't understand. People have been trying to simulate this with computers for 30 years, and obviously computers have gotten a lot better, and we know more about algorithms and about the hydrodynamics involved and all the different effects. But we still haven't been very successful in getting supernovas to explode in computers. But in the sky they do. And you guys don't remember, do you? But I do. In 1987, it was an exciting year for physics. Supernova 1987A exploded in the South Magellanic Cloud, close enough for you to see it if you were in the southern hemisphere with your naked eye. And neutrinos came flying out, and neutrino detectors on Earth detected them. And we were able to check that the number of neutrinos being emitted by the star is consistent with the theory I've been describing. We can estimate how many neutrinos should have escaped, what kind of energies they should have, and that was consistent with what was seen, although only a small number of them were detected. Unfortunately, one of our best neutrino detectors was turned off that day, because you never know when a supernova is going to come along. We have better ones now, so the next time we'll be ready. Nobody knows exactly how often supernovae occur in the Milky Way. Maybe once every 30 years or so. It's a typical estimate. Could be from 10 to 100, I guess, years until the next one. But we'll be ready. I hope. Okay. And of course, there's one other thing, I guess, to finish this story. There's a Chandrasekhar mass for neutron stars, too. And we can estimate that in order of magnitude kind of the same way. Now, how do you think the Chandrasekhar mass for a neutron star would compare to the Chandrasekhar mass for a white dwarf? A lot smaller, a lot bigger. It's about the same, because the mass of the electron wasn't in our formula. Why not? Because we considered a relativistic electron. The mass didn't matter anymore. So the Chandrasekhar mass for neutrons, we can consider that with the same logic. Eventually, the star gets heavy enough that the neutrons become relativistic, and then we can estimate, when the GM squared beats this. Now, of course, there's a little bit of slop in here because I use mass over the mass of the proton for or the mass of the neutron for the number of particles. But when it's becoming relativistic, that's pretty good in order of magnitude. If you really want to do the estimate right, it's harder than what Chandrasekhar had to do, because this is nuclear matter and it's got strong interactions among the nuclei, and we don't understand very well how to calculate that. But people have tried, and the estimate, I'm not sure. I should have looked up a more up-to-date estimate, but the Chandrasekhar mass for neutron star is actually something like 3 solar masses. Now, it's a little bit bigger than the Chandrasekhar mass for white dwarfs. So there's a region of mass where we can't have white dwarfs, but we can have neutron stars. But they, too, eventually get so heavy, the neutrons become non-relativistic, they go unstable, and then what happens? When the mass is bigger than the Chandrasekhar mass for a neutron star, nothing can stop the collapse, and we get a black hole. And, to estimate in order of magnitude, the the size of a black hole, its gravitational attraction is so strong that light can't escape from it. And so, well, this is kind of crude, but it gives the right order of magnitude. The kinetic energy going like mc squared becomes comparable to the potential energy going like gm over r. In other words, this is the relationship between the escape velocity, but now I've used the speed of light, and the mass and size of the star. And so that gives a value of r, which goes like gm over c squared. So for a solar mass, that's just a few kilometers, 3 kilometers. It's not much smaller than the neutron star, which is maybe more like 10 kilometers. And of course the reason is that well, even in the neutron star, we're pretty close to the relativistic situation, like with the white dwarfs. So that the kinetic energy of the neutrons in the neutron star isn't much different from mc squared. So it's pretty close to the radius when gravitational collapse occurs all the way to a black hole. Black holes don't allow light to escape, and still we can see them. Why is it we can see them? Yeah, I wish. Yeah, they emit radiation because of quantum effects, but that's too small an effect to be seen. But what can happen is that a black hole, a very dense, gravitationally collapsed object, can be in a binary with a normal star, and stuff from the normal star can escape, spiral around the black hole, fall into the black hole, but in the process of falling in, it forms a very hot disk of material that emits X-rays, and we can observe those X-rays. We can also see that there are very big black holes at galactic centers, including the Milky Way, because you can see there's something right at the center of the Milky Way, and stars orbiting at a very close distance quite rapidly, so there's a large mass there in the center, which is millions of solar masses. And in some galaxies, it can actually be billions of solar masses in a black hole at the center. Okay. So there's another thing that we can do that's kind of fun with quantum gases, and that is talk about Bose-Einstein condensation. So let's do that next. Bose-Einstein condensation, known to its friends as BEC. Now we're talking about a nearly degenerate Bose gas. Okay, well, we talked about a degenerate Bose gas. That was pretty easy. We have a bunch of orbitals, and at strictly zero temperature, every particle will be in the lowest energy orbital. Okay, if the temperature is small, but not strictly zero, some of the higher orbitals will be occupied, but a big fraction of the particles will still be in the ground orbital. So that's the nearly degenerate Bose gas. If it's completely degenerate, if we look at the distribution function, it's a completely sharp peak. So suppose I look at the particle number and how it's distributed in frequency space. We sort of did that for photons, although when I wrote down the black body curve, it was for the energy spectrum rather than particle number. But I would have had sort of a similar looking picture if I had said the particle number for the photons is a frequency integral of some density function, the number of particles per frequency interval. And similarly, for the Bose gas, I can consider the number of particles per unit of energy as a function of energy. And then if we're in a Bose-Einstein condensate where a finite fraction of all the particles are at strictly, zero energy, if I call the energy of the lowest orbital 0, there will be a big spike there. But then there will be something that looks like a black body curve qualitatively, although quantitatively it's different because it's non-relativistic kinematics. In the case of a black body, if I had looked at an omega as a function of omega, I'd get something that looked like that. And what's happening here is there's suppression because of the density of states factor. Remember, the density of states or density of orbitals, d of e, goes like energy to the 1/2. And so the number of orbitals per unit energy is suppressed by that e to the 1/2 at low energy. So that's what's happening here, where we're looking at excited orbitals, which are close to the ground orbital. There just aren't as many orbitals, so there aren't as many particles per unit energy. Then there's some energy range where it has a peak, because there's a trade-off. When we increase the energy, the more orbitals, but eventually the energy is getting large compared to the temperature, and the Bose-Einstein distribution function is starting to suppress the particle number per orbital. So we get a picture that looks like that. So in the Bose-Einstein condensate, we call it that if the fraction of all the particles in the ground orbital is a non-zero fraction, even as the system gets very large. Okay? And sometimes the particles that are in the lowest orbital are themselves called the BEC, the Bose-Einstein condensate. And then there's some fraction of the particles that are in the excited orbitals. All these guys are in the ground orbital, and these are the particles in excited orbitals, not in the lowest energy one. So what we'd like to do is to compute how the fraction of all the particles that's in the ground orbital behaves as a function of temperature. Just to repeat what I just said, when we speak of a Bose-Einstein condensate, we mean the following thing. There's some number of particles at a given temperature which are in the ground orbital, and consider dividing that by the total number. This is number in ground orbital and this is the total number. And then imagine taking the limit of a large system. So if this is a non-zero constant, if it doesn't go to zero, it then goes to infinity. That's a Bose-Einstein condensate. Some fixed fraction of all the particles are in the lowest orbital. Okay? So how many particles are in this ground orbital? It's just one orbital. As I said, I'll define the zero of energy so that the energy of the ground orbital is zero. What's the expected number of particles in the ground orbital? It's our distribution function evaluated at 0. So the distribution function for bosons is e to the e minus mu over tau minus 1. But we're evaluating that where epsilon is equal to 0, the energy of the ground orbital. So it's just a 1 over e to the minus mu over tau minus 1. We want to consider the case in which this is a huge number. We consider a very large system with a finite fraction of all the particles in the ground orbital. So that means this is much bigger than 1. It's 10 to the 22 or something like that. So that means that the chemical potential must be extremely close to 0. Okay? So, in other words, the denominator has to be very close to 0. The exponential has to be very close to 1. That means it's a very good approximation to expand that exponential and just keep the constant and linear terms. And so this is equal to tau over mu, but with a minus sign when I expand the exponential to an excellent approximation. And that's equal to the number of particles in the ground orbital. So if I want to have a number of particles n0 in the ground orbital, I choose the chemical potential, mu, I choose minus mu to be tau over n0, or if you want to say it in terms of the activity, lambda e to the mu over tau, when n0 is very large, is 1 minus mu over tau, or 1 minus 1 over the number of particles in the ground orbital, which is, for a large system in a Bose-Einstein condensate, this is a huge number. That's extremely close to 1. Okay? So, if we're in a Bose-Einstein condensate and the system is extremely large, we can consider the activity to be 1. And then,
Where's the step you get that's larger than much larger than?
this is the number of particles in the ground orbital.
Okay.
The distribution function when the energy is 0. And so E equals 0, and it's much larger than 1 because I'm considering a Bose-Einstein condensate. So that's telling me that the chemical potential has to be very close to 0. I can expand this exponential, and this is essentially minus tau over mu. That's equal to this very large number, the number of particles in the ground orbital. And so for some non-zero temperature, mu is just below 0, but very close to 0. And the activity is very close to 1. Now what we'll do is we'll do a self-consistent calculation. We will, assuming the activity is essentially 1, calculate how many particles are in all the excited orbitals, excluding the ground orbital. And that will have to, if we really have a Bose-Einstein condensate, that will have to be fewer than all the particles n. The ones that are left over are the ones in the ground orbital. Okay? So in that way we'll be able to calculate as a function of temperature what fraction of the particles are in the ground orbital. So we'll compute number of particles in excited orbitals assuming the activity is essentially 1 because n0, tau is very large. And then we should find that the number of excited particles divided by the total number, the fraction that are excited, will be less than 1. So what's left over that's not in the excited orbitals will be the ones in the ground orbital. N is equal to the number in the ground orbital plus the number of in excited orbitals. So the fraction in the condensate, the fraction in the ground orbital, will just be 1 minus the fraction in excited orbitals. And that's how we'll figure out, as a function of temperature, how many are in the ground orbital. Okay. So, as usual, for the excited orbitals, we'll convert the sum over orbitals weighted by the distribution function to an integral over energy. So the same picture again, I'm just drawing it again. Here's 0 energy. These are the excited ones. We want to figure out how many there are. Whatever's left over will be the ones in the ground orbital. So the total number of particles when the temperature is tau, I'll write down the formula for general activity, but then we'll set lambda equal to 1 later on. But we might want this formula available in case we need it later. We're going to integrate from 0, the energy of the ground orbital, up to infinity, density of states per unit energy, dE, distribution function, which depends on temperature, chemical potential, and energy. And we know what the density of states is. I'm going to set the spin factor equal to 1 because I'm going to consider spinless bosons. And these are bosons now, they have integer spin, and I'll consider the spin 0 case. So for spinless bosons, the spin factor is 1. No spin degeneracy. And as we computed last time, the density of states, or density of orbitals, is volume divided by 4 pi squared, 2m over h bar squared to the 3 halves, times energy to the 1/2. And the distribution function is the Bose-Einstein distribution. And I'll write it in terms of the activity, which is e to the mu over tau. So it's 1 over lambda inverse, that's e to the minus mu over tau, e to the epsilon over tau, minus 1 for the distribution function. So let's just write that again, substituting in, as I've indicated, the total number of excited particles from the density of states. I have volume over 4 pi squared, 2m over h bar squared to the 3 halves. Then I have an energy integral with the factor e to the 1/2 from the density of orbitals, and 1 over lambda inverse e to the epsilon over tau minus 1. So I'd like to convert that integral to a dimensionless integral. Let's let x equal energy divided by tau. So I can write this as tau to the 3/2 dx x to the 1/2. And the exponential is e to the x. So I take out a tau to the 3/2, and now we have 4 pi squared in the denominator, volume in the numerator, 2m over h bar squared to the 3/2, temperature to the 3/2, integral dx. We're integrating from 0 to infinity, x to the 1/2, divided by lambda inverse, e to the x minus 1. So this is some dimensionless function of the activity lambda. But if we really have a Bose-Einstein condensate, as I've said, the number in the ground orbital is extremely large. That means we can take the activity to be essentially 1. So we evaluate I of 1, which is what applies in that case, and it's just a dimensionless integral. And now I can get rid of the lambda by setting it equal to 1. So that's some convergent dimensionless integral, and I've always enjoyed writing this integral as 1.306 times the square root of pi. And the reason I like that so much is because I would like to use our old friend, the quantum concentration, to express the number of particles in excited orbitals. So remember, the quantum concentration we have defined as mass times temperature divided by 2 pi squared h bar squared to the 3/2. And I've pretty much got that here because I've got a mass to the 3/2 and a tau to the 3/2 and an h bar squared to the minus 3/2. But the pi's are a little bit screwed up, and the 2's, because this is actually a... that's not right. It's not 2 pi squared, is it? Isn't it 2 pi? And so there's actually a pi to the 3/2 in the denominator in the quantum concentration, but I had a pi squared there, and so that's why I wanted to take out this square root of pi. And then there's the 2's almost work, except there's an extra factor of 2. So if I divide by the volume, the number in excited orbitals per unit volume, the excited concentration as a function of temperature, I can write as 2.61. It's that 1.306 times 2, and then I have a factor of the quantum concentration and Q. And that formula is correct if the number in the ground orbital is a very large number. And the number in the ground orbital is a very large number if the concentration in excited orbitals divided by the total concentration is less than 1. So in other words, I guess we don't need that anymore. formula applies. If the number in the ground orbital per unit volume divided by the total number per unit volume, which is a 1, minus the concentration in excited orbitals divided by the concentration, is positive. Okay? And so there will be a value of the temperature such that, I'll call it tau Einstein. This will be true, this condition will be satisfied, true if tau less than tau sub e, the Einstein temperature, I find the Einstein temperature by setting NE over N equal to 1. Okay? And if the temperature is less than tau Einstein, NE over N will be less than 1. Because NE over N is proportional to tau to the 3/2, increases with tau. So from NE of tau Einstein over N equals 1, or I guess that's right. We can figure out what tau Einstein is. Tau Einstein, since this is just equal to 2.61 times quantum concentration over concentration, I set concentration divided by quantum concentration equal to 1 over 2.61. This is the expression for the quantum concentration. So the Einstein temperature is equal to 2 pi h bar squared divided by mass, concentration divided by 2.61 to the 2/3. Okay? Well, as we've discussed before, when the concentration is equal to the quantum concentration, that means that the typical separation between particles is comparable to the de Broglie wavelength of a particle with temperature tau. So the gas starts to condense when the particles are dense enough in that sense, where their wave functions are starting to overlap. Okay? When the temperature is less than the Einstein temperature, we've seen that the fraction in excited orbitals scales like temperature to the 3/2. So I can write the concentration due to particles in excited orbitals divided by the total concentration as tau over tau Einstein to the 3/2. So it goes to 1 when tau reaches tau Einstein. It scales like tau to the 3/2. So add 0 temperature, everybody's in the ground orbital. The fraction in the excited orbitals, number excited divided by total number, turns on like tau to the 3/2, reaches 1 at tau Einstein, and then the number in the ground orbital is just 1 minus this, so it just kind of looks like that. It's a 1 at 0 temperature. As we crank up the temperature, it declines, and it hits 0 when we reach the Einstein temperature. At higher temperatures, the fraction in the ground orbital is no longer a constant fraction of the total number of particles. Okay.